Great. Welcome to our next quantum marketplace, metrology and control for quantum computing. I'm Mark Whippich. I'm the leader and moderator of the quantum marketplace, and this is going to be an exciting event where we're going to get into the various aspects of metrology and control systems for quantum computers that are on the horizon. First of all, I'll give some updates, then just a quick overview and trends, and then we'll get into the exciting lineup, and then a spirited roundtable panel discussion. So what is the quantum marketplace? It is a place that raises brand awareness, facilitates collaborations, deals, and partnerships. There's both a web directory at the QDC website, which if you click on the company names there, you'll see a description of what they do or link to their website. And if there's a pink icon, that means they've already presented in the quantum marketplace. Also, there's a YouTube channel where these webinars are, posted in basically video processed and posted there for future viewing. Okay, so this is going to be, as I just said, recorded and put on YouTube after. So today we have NIST, NPL, which is the National Physics Laboratory in the UK. We have Zurich Instruments, Qblox, SEEK, and Rigetti. So in terms of the overview and trends, if we start thinking about metrology, so measurement and control, so controlling these systems for quantum computing, we're going to be covering areas of, there's different modalities, of course, in quantum computing, say 8 leading modalities at this point, and focusing a bit more on the superconducting, the spin qubit, and the single flux quantum side, and sort of, touching on topics of third-party testing, off-the-shelf turnkey solutions, or do-it-yourself, as some of us call DIY, or purpose-built, and more. So, in terms of the metrology, NIST and NPL are very active in this area for quantum computing, working on various components, characterizations, standardizations, often working with companies to help them with their strategies in terms of metrology, because if you can't measure it, good luck scaling it, right? Zurich Instruments and Qblox are a number of companies in the space that provide off-the-shelf turnkey solutions for control. They'll, of course, expand on that in their presentations. SEEK now, it's a quantum computing company, but also it has control chips that it's working on that are purpose-built that can also be used for control in other platforms, other quantum computing modalities. And then Rigetti is doing a DIY approach to their control systems. So Josh will go into that. And then also SEEK and Rigetti are both quantum computing platforms. So, we'll hear a bit about that too. Okay, so in terms of the metrology and control for quantum computing lineup today, we have Joe from NIST, we have Sasha from NPL, we have Tobias from Zurich Instruments, we have Bilal from Qblox, we have Matthew Hutchings from SEEK, and we have Josh from Rigetti. And with that, I'm going to ask Joe to share your slides.
I'm Joe Amatato. I'm from NIST in Boulder, Colorado. Today, I'm going to give you a brief spiel about my perspective as a research scientist who has been developing RF and microwave tools for efforts in superconducting quantum computing. If you know about NIST, you might associate us with metrology or the science of measurement, but this isn't all we do. The T in NIST stands for technology, and since we're part of the U.S. Department of Commerce, much of what we do is focused on developing different technologies that support U.S. industry. So as such, we have major research efforts in both basic and applied aspects of quantum information science, including communications, sensing, and computing. So I'm situated at the Boulder NIST campus in the Advanced Microwave Photonics group, where we pursue research in quantum computing, optomechanics, and supporting technologies like low noise parametric amplifiers and cryogenic RF microwave component characterization. This last part, characterization, it's one of the less glamorous parts of our research, but it is super important. In the diagram on the right, we have a cartoon of a typical control and measurement chain. And what you'll notice is that the thing we think of as being quantum, the part with the qubits, is actually a very, very small part of the system. The rest is comprised of familiar microwave components, cabling, attenuators, circulators, isolators, connectors, and amplifiers. Part of understanding the physics of the quantum devices that we measure is actually understanding what this environment does and how it affects the devices we measure. And so we have to understand all of that very precisely. So as part of our research, we have over the years refined tools to understand this microwave environment very well. So one of the interesting aspects of a typical microwave measurement setup in superconducting quantum computing research is that they're often, we're using components that are not actually vetted for cryogenic operation. They're often just off-the-shelf components purchased from popular vendors. So there are a lot of things that can change when you place them in such an extreme environment: dielectric constant, loss tangent, things that can go superconducting, et cetera, just because they're getting cold. Because of this, you can't measure their microwave characteristics at room temperature and expect them to be the same at very low temperatures. So likewise, many devices like solid state and superconducting amplifiers only operate well at very low temperatures. But even simple things like measuring scattering parameters are difficult to do because of the extreme environment that we're placing them in. And so an example that I'm showing here, my group demonstrated several years ago now, methodology for measuring scattering parameters at 20 millikelvin using electromechanical switches and TRL standards at the base plate of a dilution refrigerator. So it's not too different from what happens inside a commercial VNA, but we've extended it to the extreme environment of a dilution refrigerator using measurement wiring that we usually use for quantum research. If you look up the paper we wrote on this, you'll see a simple example where we de-embedded the scattering parameters of a double junction circulator at 20 millikelvin. This is one of the workhorse components that we use for our measurements. So understanding its performance very well can inform how we structure our measurements and analysis. So as another example, everyone in our field relies on some sort of low noise cryogenic amplifier to do their measurements. This might be a cryogenic HEMT based amplifier, maybe combined with a lower noise superconducting parametric amplifier. One of the most important performance metrics of these amplifiers is the amplifier added noise, or the noise figure. But measuring the noise figure in some of these amplifiers is exceedingly difficult, especially when we talk about parametric amplifiers that have extremely low noise figures. One of the things that we've worked on in our group is noise measurement methodology using tunnel junctions as a self-calibrated noise source. All the amplifier noise performance measurements that you can think of require a well-defined noise source at their core. And this fills that role very well, especially since it's extremely simple and can be operated in a cryogenic environment. Lastly, I wanted to touch on the fact that there are many other aspects of cryogenic operation that we often don't talk about in this environment, but that good characterization tools can inform. So you might imagine that maybe the robustness of a microwave device is an issue especially when you thermally cycle it from room temperature to low temperatures repeatedly. You might ask how various other material properties or microwave properties change at cryogenic temperatures. And you might even ask other higher order questions like how do different materials thermalize at millikelvin temperatures, and how can I do that better? So before I end, I wanted to point out various resources and references that if you're interested in learning more. With the QEDC, I helped author a report that details a lot of the topics that I've touched on here, especially in the context of scaling to larger cryogenic quantum computing systems. So it's a great resource. If you're a QEDC member and have access to this, I suggest you take a look. The other thing I might show you flash really quickly is just some references to some of the things that I've shown you here. I'm happy to say that, so the stuff on the left is stuff from my group. Some of it's kind of dated, but I'm pleased to say that in recent years, there's been a lot more work in the same vein by other groups around the world, and expect that to continue to grow. Let's see. The other thing is I should mention I'm at NIST. In addition to my group, there's a larger internally funded effort that aims to cover and expand on characterization. If you're interested in learning more, I have a view URL over here. The point of contact is this guy, Dylan Williams. This effort is mostly aimed at developing in situ cryogenic wafer probing techniques for large scale quantum computing systems, but many of you might be interested. So finally, my group doesn't really focus on these topics exclusively. We are mostly basic research, but we are mostly interested in detailing the basic methodology for doing this kind of thing yourself, And we've published we've written several papers on this topic. However, I understand that a lot of companies have expressed a need for accessing this kind of expertise, and that sounds like you. I'm happy if you just reach out to me directly, and I can try to contact or connect you to other people, either through the QEDC or at NIST or elsewhere in industry that might help you get started. So that's all I have. Thanks.
Thanks, Joe. Sasha.
Hello from London. Please note that throughout this presentation, I will be using QR codes in lieu of references, so have your phone cameras ready if you are interested. And with this, I begin. The UK has a thriving quantum ecosystem catalyzed by long-term national strategy and very significant investment. There are already at least 160 companies active in the quantum sector, primarily SMEs. NPL is the UK's national quantum, UK National Metrology Institute with a remit broadly similar to NIST. The Quantum Metrology Institute within NPL was specifically created to play a major role in supporting the ecosystem with measurement expertise and facilities needed to test, validate, and ultimately commercialize new quantum technologies, as well as lead the UK on the development of quantum standards, help train and upskill quantum workforce. Our program covers all aspects of quantum technologies, starting from evaluation of quantum materials, development of most accurate quantum electrical and frequency standards, all the way to design and testing quantum sensors, providing confidence in quantum secure communications and quantum computing. In quantum computing, we cover many of the major platforms, including spins, ions, and you can see one of our microfabricated ion traps. But today I will focus specifically on cryogenic technologies and superconducting qubits. Performance of quantum computers is determined by how much quantum information it can encode, how quickly and how faithfully this information can be processed. Advancing on all these fronts will eventually lead us from today's few and noisy quantum bits all the way to network quantum computers. In the following, I will give you some examples of how NPL's work contributes to improving each of these parameters. It also helps establish benchmarks to confidently compare various hardware. NPL collaborates widely with various UK stakeholders as well as international partners, including leading national metrology institutes, and has already helped numerous companies to innovate. So this is basically to reiterate what Joe has said about electromagnetic calibrations. Qubits are controlled at millikelvin temperatures by electromagnetic pulses, which need to be precise in amplitude, duration, and shape. Electromagnetic metrology at room temperature is very well established, and we work, as NIST does, to extend it to millikelvin temperatures, which is necessary to be able to characterize the whole infrastructure needed to operate qubits. This includes active and passive cryo-electronic devices, cables, interconnects, quantum and RF integrated circuits, flux quantum electronics, cryo-CMOS technologies, quantum hardware packaging, parametric amplifiers, etc. In relation to the scaling up of superconducting chips, we work very closely with partner fabrication facilities, such as the Superfab at Royal Holloway, University of London, to enable reliable high throughput process metrology. This particular facility is dedicated to superconducting quantum technologies in support of the national program, and is heavily used by UK companies and other universities who directly benefit from the metrology suite deployed by NPL. I will spend the last couple of minutes discussing how we can help solve one of the major problems facing superconducting quantum computing. In this slide, you see variability of qubit relaxation time, one of the main parameters characterizing coherence in one of IBM processors and one of our own transmon qubits. While on average, the qubits have a very decent T1 in hundreds of microseconds, crucially, at times, T1 is almost zero. The qubit is alive and kicking, but intermittently. And every time it is more dead than alive, one needs to recalibrate the whole processor. It is widely accepted that the cause of this problem is incidental two-level systems, or TLS, some kind of atomic scale defects which strongly interact with our main man-made two-level system, the qubit. We collaborate widely, most notably with one of DOE quantum centers, Fermilab-led SQMS, to understand and address this problem. We do it by developing new kind of materials metrology, where the materials are studied in their native environment of millikelvin temperatures and in the regime of single microwave photons. Some examples of our work you can see here with references to a couple of recent papers. Finally, if you want to know more about the role of NMIs in the quantum era, I refer you to a paper which I wrote with colleagues from several NMIs, including NIST. And if you want to engage with us or indeed with our UK partners on any of the topics presented today, please give me a shout. Thank you.
Thanks, Sasha. Tobias.
Hello, everyone. I'm Tobias. I'm the product lead at Quantum Technologies at Zurich Instruments. And what we do here is we help build the quantum computer. And essentially, the way that we do this is by selling quantum computing control systems to research groups and quantum computing companies, and essentially as collaborators rather than suppliers, drive with them the roadmaps towards better qubits and ultimately towards quantum error correction. And our instruments, they can control readout and feedback on superconducting qubits and also spin qubits. And therefore, we position ourselves sort of just above the quantum device in the stack. And with our Lab1Q software solutions, we can then attach to the higher levels of the stack, essentially by continuously sort of continuously going up in stack and expanding, or essentially hiding the complexity of the synchronization and the complicated digital signal processing tools. And we do this to the extent that even a theoretician can now program, for example, in Qiskit, I don't know, a VQA, and then essentially execute it through the whole stack on our devices, and then ultimately controlling a QPU. And something which we firmly believe in is that this part of the stack, this needs to be as open as possible. So we supply this under the Apache license, open source. We don't charge for it because we believe really that a lot of the value is generated by essentially modifying the software, I don't know, attaching to other software solutions, integrating them into their own stack, or then co-designing part of this software together with the QPU. So we don't charge for this, but we actually make our living by selling the instruments, and we do this successfully because people believe that we know or trust us that we know what we do. And this is partially the reason why that we have been in the field for sort of the last 5 years now, and since then have sort of built up proven long-term partnerships with some of the leading companies and institutions in the world in this field. So, for example, ETH Zurich, IQM, Atlantic Quantum, Intel for spin qubits. And what they do is they really help us to design and make the right decision for the new features and new instruments. And an example here is the QHub, which is sort of a new controller which we recently launched, which can help you decode syndromes for quantum error correction codes. And the question we had to solve here was, okay, how do you build up the architecture? And do we go with a distributed system like many others do already, or do we stick with the star-like architecture? And we decided to stick with the star-like architecture because this is really something which will not impose structural or architectural limitations research on error decoding and for the next few years. So what can our customers do? Well, on the one hand, they can, of course, do computing at scale up their system to larger and larger numbers. Here's a few systems that we have been supplied or plan to supply over the next years. And these customers then can do, I don't know, like ETH built the first logical qubits for superconducting qubits in the surface code configuration, or SUST recently broke even with their bosonic qubits. But we also understand very well that you cannot really drive the scaling roadmap without understanding the technology and metrology parts on the few qubit level. And this is, for example, where IBM made record short single qubit gates, or we use our lock-ins, which we also supply to lock onto microwave resonators with, in this case, a Pandora hole lock, and then do sort of look at fluctuations of this resonator and then learn something about the material. And the important thing is here that our system is modular, so you can essentially shift or cross this border at any point in time, because we invest a lot in forward compatibility, even across generations. And this brings us already to the end here. So what we generally look for? So we look for access to the labs, partnerships, collaborations with customers, both in industry and academia, because we really want to feel the pain of the researchers which are sitting in front of these machines and trying to understand and make sense of them. And because we're also a company from scientists for scientists, as we always say, we're always looking out for cool science and engineering challenges and really new chances to learn and grow together. So yeah, with this, please challenge us. That's it.
Thanks, Tobias. Yep. Thanks, Tobias. Okay, Bilal.
Hello, everyone. It's a pleasure to be here. My name is Bilal, lead application scientist of Qublox, and I would like to talk to you about our scalable qubit control and readout electronics, which are fully integrated. So for an easy start, Qublox is a spin-off from QTech, based in Delft, the Netherlands. Since our spin-off in 2018, we are stably and constantly growing. Our team now has reached to 80 people, and since then we have been supporting many labs all around the world. So together with our partners and collaborators in Delft and all around the world, we are happy to be contributing into a successful quantum ecosystem. So what is our mission? Here is a very known graph. On the x-axis, the number of qubits, y-axis, the error rates. And in 2023, we are roughly here, very quickly approaching a higher number of qubits. And there are two main goals in the industry currently. So one is to reach to NISQ era, and the other one is to reach fault-tolerant quantum computing, where the quantum advantage can be exploited. So as Qublox, we provide solutions for today for scalable qubit tuning, and these solutions will enable you to run NISQ algorithms in the near future. And we are also contributing into projects for fault-tolerant quantum computing. So where do we stay in this big picture? So here is the known figure, quantum chip at the bottom of the stack, living in the cryostat for superconducting and spin qubits. And there are room temperature electronics and the software. So Qublox starts with the abstract idea of an experiment that can be represented as a quantum circuit. And then, of course, it's transferred into a Python code that can be understood by the electronics. And in the end, the pulses are executed at the outputs of the electronics where qubits will see. So Qublox sits in the room temperature part of this full stack. So how is our equipment is built up? To explain the fully integrated architecture, what you see on the screen is an example army of electronics that people have used to control about 20 transmon qubits. So it consists of many AWGs, readout analyzers, IQ mixers, and so on. So this set of electronics can now be integrated into a single 19-inch rack. So our system, our cluster mainframe, is fully integrated. It is scalable and modular. So what do we mean by modularity? We have 4 different modules, and we have separated them into 2 different frequency regimes. One is the baseband regime. So the 2 modules that you see on the screen have inputs and outputs from 0 to 400 megahertz. And we have 2 other modules that can directly input and output in the RF domain from 2 to 18.5 gigahertz. So these 4 modules allow us to configure and, if necessary, reconfigure the system for the needs of superconducting qubits, to do single qubit gates, 2 qubit gates, multiplex readout, and so on. It can be used for spin-based qubits for all the functionalities and operations needed for these systems. And it can be used for optical setups such as ND centers and trapped ions. So it's a modular architecture, but we want our electronics to act as a monolithic system. And this is managed by our proprietary sync and link protocols. These are hosted by the backplane, which also has a digital architecture. So the sync protocol allows to synchronize all the outputs and inputs in the cluster mainframe below nanosecond accuracy with a picosecond jitter. And the link protocol allows fast scalable feedback. It's the distribution of the measurement outcomes for active reset type of operations or for quantum error correction. So here we provide all-to-all connectivity, meaning that up to 80 control channels can be linked to up to 40 input channels within the same time window of roughly 350 nanoseconds. So analog performance is very important for us. I'm not going to go into detail for the time being, but we strive to provide very high spurious-free dynamic range for the RF signals, very good phase relation between different output and input channels, very low 1/f noise, and great temperature stability, which is the drift value shown in the bottom right part. So apart from the hardware, of course, we have software solutions. And for this, we have 2 different layers. One is Q1ASM. This is our assembly language, in a way, for the Q1 sequence processors. So the Q1ASM allows you to control the FPGA at the very lowest level without going into detailed FPGA programming or VHDL programming. So that's the low-level access. In a way, it's non-intuitive if you look at it from the physics side, but it allows you to control, very fine-tune your parameters in the electronics. And on top of this, we have Quantify, which is a complete software package. It does basically everything for you. It does measurement, orchestration, data analysis, data acquisition, and so on. So this is open source, but professionally maintained by us and our partner, Orange Quantum Systems. And it's based on QCODE's parameters. So any other hardware in the field which has QCODE drivers can be used with this Quantify software. So we are also part of some key projects. We are working on real-time decoders to reach for fault-tolerant quantum computing. We are part of Quantum Internet Alliance to connect Europe over quantum networks. So we are partnering with academic labs and industrial partners. We develop and provide hardware to them. And we are also partnering with Kilimanjaro in Spain to integrate a quantum computer in Barcelona Supercomputing Center. So with that, I would like to finish my talk. Please feel free to reach out to us via hello@qblocks.com or via my email, bilal@qblocks.com. Thank you very much.
Thanks, Bilal. Matt.
I'm Matt from Seek, and we're building solutions to scale quantum computers energy efficiently. So that means for us kind of 4 core principles that I'm going to talk through in this brief section. So firstly, we believe that quantum control should be on chip. And then ultimately, we also believe that quantum computing should be integrated as seamlessly as possible with all other compute technologies to create a heterogeneous platform to run algorithms. We also recognize that any unique system needs a unique platform in order to run it, and that needs to be as open and as accessible as possible to any user. And for us, most excitingly, the systems we're developing are ultimately compatible with any kind of quantum computing system. So I'm going to talk a little bit about how that operates in here. So firstly, what are we doing to build a quantum computing system on a chip, and what does that mean? Well, you've seen a lot of boxes today that are at room temperature controlling qubits. In our case, all of our control and readout for qubits is on chip, integrated with the qubits. And we could do that here. We've got this is a picture of our chip for a Seek Orange, which we're releasing this year at the end of the year. And here we've got all of the control and readout you need for a set of qubits integrated with those qubits. And we can do that because we're controlling qubits fundamentally differently. So today, in order to control qubits, at least superconducting qubits and spin qubits, you need RF drive. And what that means is you send RF pulses to your qubits, and that does the kind of high fidelity qubit control. And in order to achieve ultra high fidelities, you need to have very precisely shaped qubit pulses and very precisely timed qubit pulses. And what this ends up with is you need 14-bit AWGs in order to actually build these pulses with high fidelity. In our case, we actually just directly digitally control our qubits using a technology called single flux quantum logic. And this is based on superconducting circuits that can be clocked incredibly fast. So we clock our circuits in hundreds of gigahertz. And because they are superconducting and because they can be clocked so fast, we literally can just use individual delta pulses of very precise energy. It's always fixed by the flux quanta, and send those to our qubits. And because we can precisely time them, we can step the qubit along the block sphere and do any arbitrary rotation with very high fidelity. And in doing so, we can get away with something more like a 7-bit circuit to do all control and readout of a qubit. So ultimately, because we can do superconducting digital control, we end up with a system that's orders of magnitude lower heat dissipation than the equivalent RF electronics. And because of that, that allows us to integrate it on chip with qubits in a way that actually maintains the quality of the qubits, which is critical to scaling. And then because we're on chip, now we can do some really cool stuff to lower the IO overhead, like multiplexing, or we can do digital readout on chip, digitization, and all of that can be paired into a single thing to be able to do on-chip error correction and detection. So yeah, some really cool stuff. And then ultimately, once you've got a chip-based architecture, now you can integrate with other digital chips very efficiently. So some of you may have seen our announcement with NVIDIA early last week, where we talked about how we're doing the first chip-to-chip integration of our QPUs with NVIDIA's GPUs. And we're doing that because ultimately the future of quantum computing, we've seen a lot of this in the talk today, needs to be in the data center. So this is where users are going to want to access heterogeneous computing, CPUs, GPUs, and quantum. And NVIDIA are making incredible strides into making their GPUs accessible. So by partnering with them, we can get a leapfrog of our technology to support those kind of systems. And so, as I said, we're developing the industry first kind of chip-to-chip integration. And because we're chip to chip and because we're digital, we can do this with incredibly low latencies and very high bandwidth. And actually, one of the challenges of scaling analog technologies is the bandwidth needed to run qubits is enormous, terabits per second. But by being digital and digitizing on the chip, you can bring that down massively. And also, when we talk about latencies, we talk about nanosecond latencies, not microsecond latencies. And all of that delivers ultimately heterogeneous compute for some pretty cool applications. Now, the next thing is all of this needs some software to run it. And we've built from the ground up our Seek platform. Now, this runs our full stack quantum computing reference systems, but it also is entirely modular. So anyone can bring it into their own platforms to be able to take full advantage of our chips. So this is an exciting tool to ultimately make our chips accessible. And the reason we want to do that is because our chips are compatible with any quantum computing system. And so, if you're in superconducting ion traps, superconducting or spin qubits, you can actually take full advantage of our control systems and readout systems. But if you were even in modalities like ion traps or photonic systems, you can take full advantage of our readout on-chip readout. And we see this is ultimately critical to get to real-time decoding and error correction. And this is not just real-time, outside of the fridge. This is real-time integrated on-chip with the qubits and co-processing there and there. So ultimately, this is building a fully integrated quantum computing system, which we think is the only way to really scale up in the industry. So yeah, with that, I'll say thank you.
Thanks, Matt. Okay, Josh.
My name is Josh Mutis. I'm the Director of Quantum Materials at Rigetti. And I do a number of things, but one of these is trying to basically figure out what limits performance and adds defects to superconducting qubits. And I'm going to start here by saying, and kind of echoing something that was said earlier, but like loss and defects in superconducting qubits is a grand challenge in the field. We know that there's this kind of boogeyman, a two-level system, but we don't actually know what it is. And we have to constantly be trying to find that and increase the lifetimes of our qubits while making them more scalable and better. And like was mentioned earlier, we know that measurement outcomes empirically vary in time. They vary from cooldown to cooldown. They vary from device to device. So we need to be able to cast a really wide net in terms of materials and processing techniques to solve these issues, but handle this ambiguity. So we have to be able to make sure that collaborative research happening at labs across the world have results that translate. And I'm going to touch on a project that we're doing to try to get at this round robin project. And what we're going to do is measure identical devices in different labs, quantify the distributions, and figure out how to make these things translatable from lab to lab. However, this requires that we have many identical things, an identical protocol for this inter-laboratory comparison. So the actual where the rubber meets the road is this SQMS-led round robin measurement project that we're doing. And this slide is a little dated because it actually includes NPL. There's several sites here across the United States, one in Italy at Gran Sasso, and then one now at the NPL laboratories that we were speaking earlier. And the goal here is pretty simple. We want to do a simple superconducting qubit characterization protocol at multiple sites. We want to quantify the impact of the environment, the apparatus, the repeated cooldowns, simply like moving the chip from site to site to see statistically what's going on here. But what this means is that we have to do the same thing in multiple different places. And one of the things that I think is particularly relevant to some of the folks on the panel here is that every lab has, almost every lab has a different set of electronics. And we want to do nominally a simple thing is measure these like headline performance specifications, T1, T2 dephasing, high frequency dephasing. But there's many details that come up in these relatively simple measurements, like the number of points that you're taking, the repetition rate, how quickly you're getting these time series of data, what the cutoff frequency is for your echo experiments, and even many more decisions on how we're calibrating the system. A protocol is going to require consistency, so we get consistent results from lab to lab, and ultimately to say like our fab where we're replicating results and trying to repeat this performance. So one thing that we've actually run into is we write a protocol and then we run into this kind of this conundrum. What do we do to make it translate from a lab that has like a Q-block set of electronics or a Zurich instrument set of electronics or a Keysight electronics? After we document the protocol, we agree on everything in a set of slides or a Google Doc. What do we do then? So we have three options as far as I can see it. We can script it in each lab's control electronics, which is kind of manual, requires a lot of expertise, is essentially re-implementing it, and that can introduce bugs. We could find one set of golden set of control electronics and actually like physically ship it around. This is lengthy, it reduces parallel, you can't do parallel operation, you run into customs, it's highly inefficient. The other option is we could just buy the identical set of control electronics for each lab. But the only kind of financial tractable thing, the value-based option here is this like kickboard, this Xilinx-based system on a chipboard, where we can like actually afford to put this in the lab. So what I kind of wanted to prompt here is like, what are options as a community? I've seen a few like open source things mentioned, but that can actually like help us come at this challenge where we need this reproducibility, we need this uniformity so that we can actually make progress in materials. And that's kind of where I'll leave it.
Thanks, Josh. All right, that was fantastic. Thank you, everybody. Okay, I want to start out with a metrology question, and I want to start out with Sasha. So how robust is the metrology for superconducting qubits today? You know, and have there been, you know, sort of in comparisons, and do we know what the metrology is essential? You know, do we know what it is?
How robust is the metrology for superconducting qubits? Well, I think it's in its infancy, really. I think we are only beginning to understand what type of characterization is needed. I gave some examples. Others gave some more examples for metrology, and the key issue is what kind of parameters we need to measure and how this informs the development of technology towards better, more robust qubits. I think that is what we're aiming for. Now, regarding intercomparisons, I think there hasn't been any, and Josh mentioned the intercomparison planned by SQMS. I believe this will be the first one, and it's very, very important because I think we need to make sure that everyone measures the same device with their very different methods and at different locations, but the answer is the same. And that is the aim of it, I believe. So I'm very much looking forward to the very first one. I know that other intercomparisons are being planned in Europe as well, but I think the one by SQMS will be the world's first.
Oh, wow. Okay, thank you. Joe.
Yes. You want me to answer the same question?
Yeah. I want you. Everybody's going to have a shot at this
okay.
one.
Well, so I think I have a slightly different view. I mean, it depends on what you're talking about in terms of metrology for superconducting qubits. If you're talking about control of 1 and 2 qubit gates, I believe that there's kind of a very well-developed tool set for nailing down figures of merit for 1 and 2 qubit gates, namely the fidelity of the various control tasks. So like 1 qubit rotations, 2 qubit gates. We have state tomography and process tomography, quantum process tomography, and gate set tomography. So that's kind of a well-developed thing. I would say that there's other aspects about qubits that I think, I can't remember who touched on it, but that we don't really talk about that often, and that is things like T1 drift or coherence time drift, things like that, and what the time scale is for that. And so if you're trying to build a big system, what's the probability that all the qubits look great at any given time? And so this is a thing that I think I've seen Rigetti talk about a bit, and I think that's a much more interesting. It's a maybe less talked about, but still critical aspect of building a large quantum processor. And so that goes hand in hand with like developing, improving things like fabrication or design to try to make, qubit stability much more robust. So I think those are interesting questions for the future, but and it should be one of those things that's kind of consistently measured in large systems.
Right. Thank you. Josh.
Yeah, I mean, I don't think I have much more to add beyond those two things. I think we know we have benchmarks that we rely on, and we have models of how those benchmarks are interrelated. Like we know how predictive coherence time and dephasing is of 2 qubit gate fidelity to some extent, for example. But I think the fact that performance varies so widely in time and the same cooldown on the same device is sort of just like an open question. So it's hard to say like we have great metrology when we can't really like tell you why a qubit can go from like 2 microseconds to 100 to 400 microseconds in a day. So we have good techniques, but I think we have a long way to go in our fundamental understanding of what's going on in these systems, from like a materials or whether it's an environmental coupling or what have you, what's going on there.
Right.
Yeah,
Thanks.
methods exist, but the question is how robust they are.
Yeah,
Right.
yeah, we're probably missing something on a systematic sense. And like I've seen over the course of my career, like just being very, very, very careful on how well shielded and isolated things like makes it better. But it's still, even in like IBM's paper, the one that Sasha showed, like there's a lot of variation in time. And it's hard to kind of come up with a reason for that that's like physically reasonable.
Right. Matt.
Yeah, I mean, I think I've got the same kind of views on we need to improve, qubit coherence and the metrology of the system, of course, because that is, we need to push up the T1s and T2s across the board. But I also think that one of the solutions to this is both in metrology and making better qubits, but also in ultimately speeding up how fast you can do any quantum operation. Because we've seen in some of our recent data that if you've got a very long gate, you are significantly more sensitive to T1 and T2. And therefore your fidelity of your gate operation jumps about, and you can track it with the changes in T1 and T2. But if you can bring that gate time right down, you can desensitize yourself to instabilities in T1 and T2. And so you can kind of break them apart. So your T1 and T2 is still jumping all over the place, but your gate fidelity is relatively stable. And then if you can do that and partner it with a very quick, say if you want to do error correction, you want to do a very quick kind of parity check sequence that can be done again well within the lifetime of the qubit, then you can again make your error correction somewhat desensitized to fidelity. So I think that's how we should do both, right? We need to both improve the control and parity checking of error correction, so that you can deal with good coherence and improve the coherence of the whole. You make the whole system better. But that's kind of my view on it. That ultimately if we can make our control faster and do things more precisely, then you can desensitize yourself from jitters in coherence.
Okay, great. Bilal.
Yes, good question. I actually don't have much to add after the answer is given, but maybe I can be more positive on the answer. I think for superconducting qubits are more established compared to other qubit platforms today. So we can still, for their fabrication, we can fabricate them with certain frequency range, within certain frequency range when it comes to the resonators and so on. Let's take transmons, for example. There are companies stably fabricating 25 qubit chips, 5 qubit chips, and so on. So I agree with all the comments, answers given, but at least from the control electronics perspective, our job is to make the experimental setup as robust as possible, or with lowest noise, with lowest drift, as good as possible, such that at least we don't contribute to this problems in the coherence time and noise and gate fidelities, but make the system as reliable as possible, such that the pulses that you apply from your electronics or from the room temperature part of the system does not contribute to the problems that you would have when you're doing your metrology and when you're doing your experiments. That's what I can add on that.
Okay, great. Thank you. Tobias.
Yeah, so essentially what I wanted to bring in a bit of a different touch, which we touched on a bit in the past or in the last statements, which is the statistics. So okay, we can learn. So if you move, for example, like in the SQMS setup, or when you move sort of a single chip and compare it in different setups, then I think we can learn something about maybe different effects or variations between the different control systems. And this is, of course, important. But in the end, how can we use this then in the end to actually make metrology better, make the superconducting mass fabrication better, and essentially getting the statistics, sort of a bulk know-how, and see what changes, for example, in the process, in the materials, can sort of really get in the end the yield better of even larger and larger systems. So this is something which we just here more and more forming, and we also see from requirements and people coming to us wanting to actually increase the throughput. So I think in this case, to approach these challenges, there's essentially these 2 points in summary now. So they're essentially getting high throughput. This goes from, of course, from the control electronics, for example. So if you cool down a 300 millimeter wafer and you have a lot of qubits, how do you get this statistics there? There you want to do simple experiments like the standard ones, which were mentioned before, T1, T2 measurements are very simple experiments, but you want to do them, execute them very fast, maybe with multiplexing and demultiplexing then at cryogenic. And then, of course, as also mentioned by Bilal, the key thing, main selling point also for us is, of course, always the comparison between one run and the next run, or getting the controller links out, avoid drifts, no IQ mixers, all of this, everything which can add variations where we actually have the control over it, which we know should at least be benchmarked to the way that it doesn't influence the outcome.
Yeah, great. Thanks, everyone. Okay, so let's go to the next one. Why would a quantum computing system solution provider work with your technology platform? So let's go right back to you. Let's go back to Tobias.
Okay, so why would a quantum computing solution provider use our technology?
Or your platform, yeah.
Exactly. Yeah. Well, okay. So what is it that we're strong for? So I think in the end, the main reason is because we help them get the results faster. I think that's the main point. So we are the experts, and we know what we're doing in terms of the control electronics. So we know how to program an AWG, and there's no black magic behind this, but there's a lot of engineering, and this is something we know. So this also goes into the question of which we might touch later, is sort of open source, self-made versus suppliers. And we are, of course, here not dogmatic, but the question is, okay, where can we add value? And the value we can do is where we believe we have sort of the universal solution, like AWG, sequencers, filters. This is where we can actually provide the better solution and not have others essentially concentrate on this. And they can then rather spend their valuable time on actually doing the cool stuff, like doing the new algorithms, doing the science, dig for the gold in terms of the quantum part. So, and this is also the reason why many of our collaborators like IQM, or they rely on our technology roadmap. They trust in us that we will not today, but even in the future, will design the right things which will help them speed up, and they can fully concentrate on where their value lies.
Okay, so you thank you for that. You opened the door there. So so your wrapped solutions today, that works for today's quantum computers. So when you're talking about IQM and others, so you're talking about, as they scale in their qubits, you're going to modify your platform. How are you looking to do that? What can you say about that?
Mm-hmm. So of course we are, and this comes back to also what I mentioned, so we are well entangled in the field, and we of course make continuous decisions, and we are very open and very transparent also with the close customers, but also generally with the public about our roadmap. So we'll of course adapt the roadmap to the needs, but we will definitely not go to one supplier and adapt only for this one. In the end, we have to make money, and there's always sort of this fine line of designing your whole electronics for one, but then have a lock-in, but then also have to sort of supply a lot of others. So where's the market values? And of course, this is one of the daily challenges that which is our bread and butter, and where we have to, which we have to do well in order to be successful, or to continue to be successful.
Yeah, great. Thank you, Bilal.
Yeah. So. Good question. There are many ways I can answer this question, actually, and but I would say I would like to start with, if you ask me this question like 2-3 years ago, then the first answer that I would give you is that because we are providing fully integrated electronics. So I had this slide where I showed like a huge set of electronics, and this was the conventional way all these solid state experiments have been conducted in the lab. So I have used similar experiments, and I'm sure most people in this talk right now, in this session right now, have used this kind of equipment. So lots of electronics, and they're not scalable. So you need something more economical, compact, scalable. These are physical features, but you also want a compact system because you don't want to deal with many cables as noise sources. You don't want to calibrate, so on. You don't want to deal with all these APIs and different softwares into your system. So you want something compact so that you don't spend so much time on this, but you only need a dedicated hardware, a dedicated software, so that you can do your experiments, spend time on your qubits. But the system, the field is evolving. So today, I don't need to mention about this because all the research labs and industry partners are now working with dedicated electronics, such as us, such as Zurich Instruments. But now, still, the field is evolving, so the needs, the requirements will change. One of them is, of course, scalability. One of them is like the modularity. So there are, as an example, there is a lab working on transmon qubits. They start with transmon qubits with, I don't know, a 3-qubit chip, but then in a couple of years of time, they would like to scale up the number of qubits to 20, 30, 50, whatever, and they will require more channels. So our solution is scalable, so you can add more modules into it, and they're gonna work in the same way. They will be fully synchronized once they're mounted. You're gonna use the same software and so on. It's an open source software, so if you wanna build something around it with different hardware or depending on like different needs of your experiment, you can still build it on top and share it with others. And when it comes to, for example, spin qubits, where silicon, germanium, or gallium arsenide is a bit off now, but there are different qubit types and there are different qubit readout and control mechanisms. And these all require different set of electronics and needs from the room temperature side. So that's also possible by choosing different modules. What I want to say here is that the solution that we provide today will be backwards compatible in the coming years as well with the improved modules or new modules that will be added in the future, and that will carry you to the NISQ era. So soon, I don't know, 3 years of time, 5 years of time, perhaps we will be working with easily 100 qubits, 500 qubits, and you will need still a compact system, a high density, high channel density system, but you don't want to buy a new electronics for this all the way from the scratch. You don't want to build up a new software. So we're building it all the way completely backwards compatible, so you don't need to deal with a new software or like a completely new device architecture.
Yeah, got it. Thank you. I go to Joe. So there's a lot of things that NIST does that, you know, in terms of metrology, third-party testing, that sort of thing. And, you know, why would someone work with you that's working in the superconducting area?
Well, I personally have a strong interest in putting the tools and the methodology in the hands of the people that need them.
Yeah.
There's also another model, which is testing as a service, which is hard for my lab because we're mostly focused on basic research. There are other people at NIST who, you know, do things like calibrations, and, you know, when you get a piece of test equipment and they say it's NIST traceable, there are people that at NIST that really focus on building those standards. I really like the idea of building tools like the shot noise tunnel junction or parametric amplifiers, things that I can give to people, and also communicate techniques that people can execute on their own hardware, things like the S parameter calibration at cryogenic temperatures. I'm much more interested in that approach because it empowers everyone to kind of do this on their own. But that being said, this testing as a service model, I think there's room for the community or for, you know, particular industry players to serve that role for other companies. especially like, if you're like a smaller component manufacturer in the microwave electronics space, maybe you make like passive devices like attenuators or circulators or whatever. It's probably not in your best interest to buy a dilution refrigerator just to go and vet your devices and
wait in line.
Right. So when we talk about people working with NIST, I think like one thing that NIST can do is guide people and connect them with people that do testing as a service, or even just tell people how to work with people, different companies, on how to do various things better on their own.
Yeah, and how about how about the whole point about working with you to say there's an area that they want to standardize, you want to standardize, you put together an agreement and you publish a paper or something together on the results to sort of push the ball forward in the community. You do that
too. I
mean,
there are lots of opportunities like that. I think especially facilitated through the QEDC, there are various mechanisms like SBIRs outside of the QEDC. But if you're a QEDC member, I mean, there have been various calls for funding proposals where industry players can connect with NIST scientists on particular projects, and so I think that's a great mechanism for doing this as well.
Yeah.
Not much else to say.
Great. Thank you. Sasha, what would you add to that, or if you have a different perspective?
Well, the perspective is really similar. The setup is slightly different in the UK. So we have various opportunities for industry to work with NPL as well. So we have a program led by the essentially the innovation arm of the Research Council, and they fund various missions and projects to which enable both industry and research laboratories to work together to solve specific problems. But we also have a way for industry to access our capability directly. So we have a program called Measurement for Quantum, which essentially gives companies direct access to NPL facilities and expertise for a limited time to solve a specific problem where this can make a real difference. And it's a very effective and efficient program that we run. So there is huge interest from industry. I believe there were something like 82 applications last year alone, and in addition, we have a bigger program called Analysis for Innovators, which gives more time for industry and NPL scientists to work together on more complex problems, and this encompasses everything, not only quantum. But I think both models are valuable, and as we see in practice, they are very well subscribed. So
yeah, great, thank you, Matt.
Yeah, and we've used those A4Is from NPL, so I can attest to their usefulness.
Thank you, Matt.
Yeah, I mean, I think I can add a bit of an interesting point to this, because we're on both sides of this. We both buy electronics and we build our own and use our own, and then we're also developing a chip-based solution to try and scale quantum computers. And so from that perspective, control is like incredibly important for a system developer. Like it's, qubits, you need really good qubits and you need really good, control systems. And that's how you build a quantum computer. And so it's so important. I think ultimately a lot of the big players are choosing to buy off the shelf components and modify them themselves in-house, because it's just so incredibly important to get it right. And they'll put the resources into doing that, which are immense. So I think that puts a big barrier to entry for anyone that wants to sell a solution to those groups. So I think the way to solve that barrier to entry is ultimately to provide something that is, gives them a really unique opportunity, to scale. So it has to be something fundamentally different to what they're doing, right? So if they can do it themselves, well, they'll do it themselves. That's the point. And also you need a solution that you can modify yourself. So I think one of the things we can offer is that from a chip-based point of view, early on we would be working with partners to make sure what we're building is really built for, optimized for their systems. But ultimately, the long-term strategy of this is that we would have IP blocks that, just like you have an ARM system, you license, I want to build this thing, and I would just license my core ARM technology to do it. You could take whatever you want from our IP library and just configure it as you need to run your quantum computer. So you can build back that flexibility that I know exactly what control I want, so I'm going to take this, and this, and build it into my system. And I guess ultimately having a chip-based architecture allows you to do that, because it's a proven model, right? That the groups want to build. If I want to build a phone, I go to Qualcomm and I license this IP, which is how I'm going to build my phone, and I build it into my system. It's a proven model. So I think ultimately, simple messages are, it's got to be better than what they can do today, and it's such an important problem. It needs to be flexible to suit their needs.
Yeah, great. Josh, I know you're doing a DIY. Why would someone do a DIY their own way or similar to yours?
So I think if you're asking me to wear my Rigetti quantum engineering hat, if you're making a big integrated system, well, I think one of the reasons is historical too, right? So we started doing this 10 years ago, before there was any industry like there is now. So we have a lot of experience and a lot of already built up infrastructure and software stack and everything. So the incremental cost for us to develop our own solution is lower, I believe, than to bring in another one. And then there's just a matter of scales. If we have we do a facility full of dilution refrigerators with superconducting qubit platforms, the added cost of a new board is less because we design everything in-house. And so we just spread that over more stuff. So making the physical boards, stuffing them, and doing all that isn't actually that much more expensive. And there's a bunch of things that pop up when you're running a system at cold, at scale, like at the 80 qubit scale or something, for a long time, that you really need the ability to change things, get your elbows deep in the electronics and figure out what's going on, because there's a bunch of subtle stuff that shows up, and you kind of need to, you can't delegate away that understanding, or else you're not going to be able to get the highest performing system.
Yeah, got it. So part of it is because you've been doing it for so long, but if you're a new company, is that a heavy lift to just get started from ground zero and doing your own?
Yeah, I mean, if I were starting from ground zero now, I would certainly not want to wait to develop our own electronics to get data. And I'm sure all of the solutions are very, very capable. And so that would be the way to go. And then you have to decide the buy or build equation.
Right.
A bunch of constraints, for sure. Depends where you want to add value, right?
Yeah.
We see ourselves as a platform, and so we want to own a lot of that platform. But again, it's a strategic decision. It's a subtle decision. It's a history-based decision. And that's only a few factors that I can think of off the top of my head.
Yeah. Okay, great. Thanks. Okay, so, how do you scale your solutions to large, high qubit count, real-time error-corrected systems? So, and what I mean by that is, so I realize this is a little bit out in the future, but, what does this look like, or what will this look like for 1,000 qubits, million qubits error-corrected? This is going to go right back to you, Josh.
Good. Yeah. So I have opinions on this. I think the answer is we don't know, but I think we need to agree on models of how that architecture is going to work. So they can be really simple models, but we have to account for all the things that matter, like thermal, electrical usage, like power consumption, pulse distortion, like just a few things off the top of my head, and like write down the figures of merit of all these different solutions and kind of do the math, because it's not obvious what wins out, where you want to put the electronics, what the consequences are in certain things. And of course, that'll be wrong because we'll be making a model of a million qubit system, not physically making it. But until we write it down, I don't know a priori that like the heat load of a piece of electronics at 4K overwhelms is a net benefit over like putting my electronics at room temperature that negates the pulse distortion things, because I haven't done the math, right? And I think until we do the math there and compare, like kind of buy into a single model like across various applications, then we're not going to kind of have a prediction.
Okay, great, thank you, Matt.
Yeah, I mean, I think the answer is that what a 1K qubit system looks entirely different to a million qubits. And I kind of agree with Josh that we don't we don't know what a 1 million qubit system, the details of it.
I had to ask, right? So
but I think the point.
I realize 1K may be more in the realm of like being able to grasp what that might look like.
No, right? Because I think we have grasped it, right? So my answer to this is, though we don't have an answer of the details, we know how to build big computers, right? We've done it. Yeah. We've done it over and over again. What we haven't built is giant, cable-based computers, right? No one's ever scaled an analog computer. We quickly went to integration on chip, and ultimately that's how we made computers. And so, frankly, no one can make a giant, large-scale analog system. So I think, when we get to the million qubit answer, we don't know the details, but we know ultimately it has to be integration, right? That's your answer. As much integration as physically possible. And, ultimately, to some of Josh's points about this, single distortion overloading of the fridge electronics. I mean, we've started to do those calculations, right? Actually, and critically, we know that if we can do the integration, then you can eliminate a lot of the pulse distortion issues and a lot of the I/O overhead. But it has to be done with that heat dissipation in mind. And at the point of our reference quantum computers is to prove that you can do integration without having to do the overloading of the fridge. So I think, ultimately 1 million qubits is integration, as tightly integration as possible. That's the answer. The details are to come, but it's all about integration. And 1K qubits, yeah, sure, we can brute force that system to, use room temperature electronics. It's proven to be today higher fidelity, right? So let's stick to that for 1,000 qubits. But I would love to see, the ideas of how you're going to go from 1,000 qubits to 1 million qubits with, different electronics here and there.
Right. Thank you. I want to go to Joe. Sasha. So Sasha, in the work that you're doing and the partners you're working with, how do you see this?
I guess very similar to what has been said. It's very challenging, so challenging that the future is hidden in the fog. But I want to add one more problem to the problems that people have mentioned already, and that is the thermal management of the quantum chip itself. So the cooling of one chip is difficult because we rely on insulating substrates and superconductors, which are very poor thermal conductors at millikelvin temperatures. Now imagine you have multiple chips. You have sort of a modular system with many chips, each containing, say, 1,000 qubits or so. And then it becomes even more complicated. And I think one solution that we are testing at the moment is the use of immersion cooling at millikelvin temperatures. I think that will be, if that is successful, that will be the future for big systems as well.
Yeah, because you have to calibrate less and other things. Great. Joe.
So some of this is, I mean, I can talk about some of what we discussed in the QEDC report that I referred to in my talk. There were a couple of, critical things that have been mentioned already that we talk about there as well. That is the input output problem. There's a fan in, fan out problem. How do you get a lot of lines in and read out a lot of qubits simultaneously? And then there's this issue of just physical footprint. The input output thing is interesting because there's an interplay, or you have to consider the thermodynamics or the cryogenic management of that whole task. Getting a lot of cables has a lot of thermal conductivity associated with it, so it's not obvious in a dilution refrigerator context. My group has explored some of this in that context by trying to drive qubit control through fiber, which is of course very high bandwidth and then very low thermal conductivity. So there are groups around the world that are like exploring these options. I might point to a paper that came out several years ago from Andreas Walrath's group, where they talk about some of these scaling issues as well in terms of like thermal management and how that scales. But with respect to the physical footprint, there's a lot of components that, as I mentioned before, we're buying off the shelf and that aren't maybe the smallest they can be. Physics can will allow you to make certain things smaller. And so like integrating things like parametric amplifiers, making the readout hardware a lot smaller, integrating all the hardware that's required for doing a readout into smaller and smaller packages. That's really interesting. And I know this is something that people have been thinking about, other people have been thinking about as well. I think once we go down that path, you could probably get, I don't know, on order of factor of 10 at least reduction in size of a lot of these physical components that we're using now that are currently discrete. So I think like that's the future. If we're, we keep batting around this idea of 1 million qubits. I want to be a little bit cautious about that. As we all know, the control problem is daunting, but as we improve materials and qubit quality, this number can drop by an order of magnitude or more, depending on how much improvement we see in qubit performance. And so I view the problem as getting solved from both ends, both at the qubit quality end, which has been going on for 20 something years, and then from the kind of control hardware and measurement hardware inside the fridge side.
Yeah. Thank you. Bilal.
I think Josh wants to say something. He raises his hand.
Oh, Josh, go ahead.
Yeah, I just wanted to very quickly, like the fan out issue is in the central bottleneck, I think, is the interconnect. Like, how can you get signals off of your chip, regardless of the architecture? So like what are those pins? What are you doing in that technology? And that bottleneck, I think, is one of the biggest limiters to like 1 million qubits. Because it doesn't matter where you put your electronics if you can't physically get signals like off of the chip at that scale. I just wanted to kind of throw that out there.
Okay, yeah, great. Thanks for that. Go back to Bilal.
Yes, thanks. So I really like this question. It's a difficult one. As already answered, we don't know much, but I agree with, of course, all the answers given. But for 1K qubits, I think, as Matt mentioned, we can actually do this with brute force with the solutions provided today. If I need to answer like what does this look like, it's gonna look massive. So what you see behind me can be put on top of each other. We can create a wall of electronics, maybe
Right.
multiple walls of electronics, and it's gonna work the same way. Like the way you control 5 qubits will be the same as controlling 1,000 qubits. It's gonna work, but it's not sustainable. Nobody would like to do that. I guess somebody will do that, but let's see. And this would be to also add something. I think this will be done at first. Quantum computers hybridize in supercomputing centers, because that seems to be the place where the value can be exploited in the near future.
Yeah, right. Right.
Yeah. And
right.
from moving from this number of qubits to further on, I think the structure, apart from this, the problems that have been mentioned before, the roadmap can depend on how we are going to do this error correction. So are we going to, what schemes will be used? Is it going to be surface code? Is it going to be something else? Maybe some new invention to create these logical qubits, because it's gonna determine the type of qubits we would like to use to scale up to million. And of course, the type of qubits and the chip will determine the requirements from the control electronic side. Then control electronic providers will also work on this. Like we are working on real-time decoders, and we would like to bring a decoder together with control electronics. They have to work really hand in hand to create a nicely working logical qubit. So for million qubit, I have no idea, but the way we do the error correction will definitely determine this.
Yeah, got it. Thank you. Tobias.
Yeah, so how do you scale it up? So I think the main thing here is that we have to ask essentially the question of the cost. So everything which is scale up will cost somewhere, or it will cost, of course, financially, but it will cost it. Where do we put, or where do we take this? So do we trade off flexibility, which brings us to the topic of standardization or performance in terms of co-design, or of course, then questions like which has mentioned before, like power consumption, price per qubit. How do we choose this? So this will be some of the critical questions which you really have to ask. Also in a much broader group, not only in terms of control electronics. And of course, we, in terms of the control electronics, we always have to ask ourselves, okay, when is a technology premature, when it's ready for commercial development? Bringing in ASICs, we can do this today, but there's just no business. There's no value in there of doing it because it doesn't add enough value. So this is sort of more on the sort of short-term incremental steps, how we go now, where we go now towards 1,000 qubits. This will work. I think even 10,000 qubits will work with this brute force approach. Flex cables and room temperature electrons can still go a long way. And currently just the whole chain and the whole value and the field is there that it currently favors room temperature electronics. And now changing, of course, to like more integrated solutions. Like SEEC or generally cryoelectronics, or this will come. This will have to come. The question is again cost. When will this transition will be? There's very good reasons and very justified reasons that you invest already today in researching and going there and trying to find out what the technologies are.
Sounds like you say it's just about money, and you have a solution, so you can help.
No. It's not about cost. It's not about money cost. It's about the trade-offs which we have to take.
Yeah, right.
It's about the trade-offs to take. So when does the systematics? So I mean, going highly integrated is something which already restricts you to a certain extent in the flexibility, right? So so when is the technology really ready that you can actually scale this up? Because of course you can find you can find a solution at some point, or for a certain group, but will it be really successful? Will it bring the the breakthrough, will it foster the breakthroughs when you suddenly take away sort of this flexibility which room temperature electronics currently gives in the performance, in the ability to change quickly? This is a question which you just have to ask.
Okay, great, thanks for that. It's fantastic. Okay, I want to go to this one. So how do you calibrate this at scale, right? So this is really a battle of, metrology versus control. One is a physics problem, metrology, and the other one's an engineering problem, control. Let's start with Joe on this.
I'm not really sure I understand the question, because if you talk to somebody that is trying to quantify how good their 1 and 2 qubit gates are, they would say that they're doing metrology, but in order to do metrology, they have to have very precise control. And so you have, again, figures of merit to judge how well you're controlling a qubit. I'm not sure that that's different than saying that you're doing
the spirit of this question was the point that until the metrology is figured out, the control is going to have more things to deal with, right? And so you got to really be able to measure things before you can actually control them consistently. That was the spirit of the question, right? So do you go off and do control systems before the metrology is really figured out and you have everything stable, right?
I think they go hand in hand. I mean, maybe one feeds the other.
It's the other, right.
But I mean, there's a lot you can do in terms of the metrology of the control instrumentation already. Things like characterizing jitter and amplitude drift and timing drift and all that stuff. And I think that's a lot of kind of well-developed room temperature metrology that people have a handle on already. So then it comes down to, how do you use that to go so I think the issue is that, you're trying to measure, say the quality of, your quantum processor or how you're doing your gates. And so the issue is that, you don't want to convolve different problems. You don't want to convolve dumb issues with passive devices or active devices in your chain with control hardware electronics, problems in the control hardware electronics, as well as problems in the quantum processor itself. And so I think this is where maybe the metrology aspect comes in. You want to go and deconvolve all these things and be able to measure them all separately, right? So but I believe that it's a matter of what's the easiest to the hardest thing. I think the easiest, and I say easy in quotes, it's the verifying or validating that your control hardware is doing exactly what you think it's doing, especially when you're trying to synchronize several control racks and getting all the timing exactly right. Then separately ensuring that all of the components that are sitting inside of your fridge that are handling or transporting microwave control signals and measuring microwave control signals, that those are all doing exactly what you think they're doing. And then at the lowest level, then I would say you can start to believe all the things that you're trying to ask for from the quantum system, in terms of that metrology.
Yeah, great. Thank you. Sasha, I know you have a lot to say about calibration, right? So
for me, the problem is slightly different, in fact. I think metrology of single qubits, metrology of the qubit control infrastructure, metrology of control systems. We are beginning to understand how this is done, how to make it robust in a robust way. So that's coming, and there is no tension. I mean, the tension maybe in the sense that metrologists do not like to work with black boxes. So when we get a device that the manufacturer says does this, and I don't want to point fingers here, but we need to understand what it really does. And sometimes it involves working together with manufacturers and getting into the nitty-gritty of the operation of these control systems. And I have to say that we've been experiencing a lot of goodwill from manufacturers who work with us, because we understand things, but they also benefit from our insights. But there is another question which is related to this, and that is how we calibrate quantum processes at scale, right? So when we have very many qubits, very many control lines and a lot of control electronics and a software layer. So I think this calls for something completely different, and that something different is basically related to software metrology, or metrology at the software level, where you develop methods to interrogate the large system, and you need to be able to interrogate these large systems at different layers of the software stack. And this is where we sometimes encounter problems, because yes, we can devise a code which would interrogate, say, cloud connected quantum computer, but we often do not have access to lower layers of the control stack. We don't understand how the gates are implemented, when the calibration, hardware calibration happens, and so on and so forth. So I think this is another area where metrology needs to develop, and it can only develop in good collaboration between hardware manufacturers, providers of quantum computing services, metrology institutes, and other stakeholders.
Right. Thank you. Bilal.
Yeah, so it's also a difficult and good question, but I also agree with Joe that they go hand in hand, metrology and control stacks. So I see this rather than a battle, a dance between these two.
I like that. Yeah. Maybe that's a better term here. But thank you.
I think the core problem here is on the physics rather than engineering. So of course there are lots of challenging in the engineering side, not only for control electronics, but for the cryostats and all sorts of cabling and so on that we have discussed in the last hour. But the results from metrology basically tell us the ways, the steps that we should take to develop the electronics, to develop the control stack. So the problem also, or the focus changes from researcher to researcher. Like if you want to work on a single qubit calibration, then you may need to have some flexible tools in your hand that you need to fine-tune all the knobs in your electronics, in your control stack, to try out different things. Or it could be that you want to calibrate in an automatized way, such that you have, I don't know, maybe you need to scale up qubits and you want to go as soon as possible to 25 qubits to run your Surface 17 code or something like that. So I would say it goes hand in hand, and we learn from each other, and the tools that we provide back to the lab with high channel density equipment, or allowing feedback, for example, the tools that researchers can easily do quantum error correction algorithms. This also gives something back to the lab, and then they try out and they see, okay, here is a new improvement. We need a new improvement on this side. It has to be faster. For example, the coherence times, and then the how long the qubit lives determines how fast we should do these feedback operations, because in the end, it's the time scale that is determined by the qubit life. So these are like many different examples from the lab that shows that it's a dance between these two.
Yeah, great. Thank you. Tobias.
I agree that it's that they go more hand in hand in this respect, or it's just the fact that more qubits will yield a worse QC, quantum computer, and in the end, the control electronics, or the classical system, is really here to be able to stabilize the flexibility or variability, and in metrology can inform us or how far we can push this, but in the end, it will be an engineering challenge. Of course, it will be limited by the physics, but in the end, it will be an engineering challenge to get it as the qubits tuned up or calibrated as close as possible to these physical limits. And you can then help with cool features to, I don't know, in terms of error correction. As soon as we're below the threshold, you can put in, I don't know, tensor algebra and two cool things. But in the end, it's a question of keeping the complexity at bay when you tune up. Or so now coming back to this example, or we have I don't know, 1,000 or 10,000 qubits, or then you have so this is 10,000 lines upwards, and then you have 1,000 pulses. Or so this is a really complex system, and if you move one pulse, it will influence the other ones. Or and this is why to keeping this complexity is really a software and engineering challenge, where it is critical to the success to have the concept, the right architectures to be able to continuously abstract from this complexity to higher levels where you can still have the right KPIs and understand how your system is actually performing. Or and this is why, exactly as mentioned also in the beginning, or this is why we think it's so critical that the flexibility in these software layers is maintained, because in the end, people will have to adapt the way they tune up their system, in which order they do the tune up, whether they start with small QPUs and then or small samples, or they do directly a cross entropy benchmark on the whole system. This will strongly depend on established performance metrics and established ways, which can be very critical or very specific to the QPU. That sort of this openness is important here. But I think it's in the end, it's an engineering challenge actually, and a complexity challenge.
Yeah, great. Okay, thank you, Matt.
Oof. Yeah, it's a big problem, isn't it? So yeah, I think Josh said this well. Like metrology is a grand challenge the industry has to solve, and we all have to work on it. But it really is. I mean, we're pushing the limits.
That's why we have NPL and NIST here to help.
Yeah,
right?
exactly.
So that's absolutely
and quantum system providers are also working on it, which is excellent. But it's pushing the limits of physics, and it's also trying to understand physics we don't understand today. And that's a really, really hard problem that will take time. I left academia because I couldn't cut the time scales you need to do these things over. So I much prefer solving engineering problems because they can be done, relatively quickly with well-known challenges. So I think we need to solve metrology, but we can't wait for metrology to get better. We have to build quantum computers that can handle the metrology challenges we have today, or can project out with the known physics. And the way to do that is to solve the engineering problem of control. And the way to do that is make we've discussed this a lot, make the whole system simpler. So the more, components you have in there, the more amplifiers you have in there, the more wires you have in there, the more the things can fail, and the more you have to calibrate out those subtle changes. Anything mechanical that goes in there has to be calibrated out. And so we need to solve that. And then it goes back to my point earlier that if you can make control really, really fast and really, really sensitive, and lower the noise floor of everything, then ultimately you can live with the coherence you have, right? The metrology you have. So what we should be doing is designing our systems to live with the metrology. So making them as fast as possible so that we are less sensitive to the limits of physics, right? So, physics is limited for there. Let's make sure the control electronics are so good that we are not limited by that physics. And then as we improve the physics, the whole system will get better. So everyone wins. But we shouldn't be reliant on waiting for the great scientists of the world to figure out physics that hasn't been figured out yet, which we totally need to do. But I'm not going to be doing it.
Which is throughout the entire quantum ecosystem presently. Okay, Josh, final answer.
I don't know if I have anything really to add beyond what my fellow panelists have said. Like it's hard. We have a lot to do on both fronts. I just say
part of the spirit of this too is the question that we were not going to have time to get to, but the question you had is really, getting back to like doing all the, you have all these different sites around the world, and how the hell do you make them all run the same?
Yeah,
right?
I think.
And so how's the metrology the same so that your control systems are the same, and how can you get them all to run the same so you can scale?
Yeah,
right?
and I think that's a different axis of scale than when we talk like where it's all one system, integrated
Right.
system. Now we have like basically a distributed system that we want to all work together. I think one of the answers to that is like, and I've heard a few things mentioned in today's talks, but like open standards to make sure that you're actually like doing the same thing in different places. So like if I can encode my protocol in a piece of software that I can deploy from system to system to system, like that would make my life tremendously easier, instead of having to kind of rely on like graduate students and staff scientists to implement like a paper protocol. And then like so that kind of thing I think would sort of bootstrap the metrology, and improve the control just by getting rid of a bunch of errors, essentially making it more rigorous.
Yeah.
So that's again like an engineering solution to a physics problem that I'm hoping to see. And then if we have like multiple open source packages to do that, I think it behooves us to kind of consolidate into one, get behind one thing. And maybe the QEDC is a really good forum for that, because I don't want to have to choose now like which open source measurement thing I'm going to use, because I might have to do it 5 times or something like that.
Yeah, right. Well, I want to thank everyone. This has been fantastic.